Hello, everyone. Welcome back. Today, I'm going to be talking about scientific notation. So, we're going to go through this paper about scientific notation, and then we're going to do a worksheet about scientific notation together. So, basically, scientists need to express small measurements, such as the mass of a proton at the center of a hydrogen atom, which is 0.000000000000000000000000001 kilograms, and large measurements such as temperature at the center of the sun, 15 million kilo K. To do this conveniently, they express the numerical values of small and large measurements in scientific notation, which has two parts. A number in which, so we have n, right here, and n is a number in which only one digit is placed to the left of the decimal place. So we have one number, and then decimal, then the rest of the numbers, and then that's it. And I should add this number. It wouldn't be zero. It wouldn't be 0.000 blah blah blah. No. For example, for this one here, it would be 1.673 for n, right? Because we want a number in which only one digit is placed to the left of that decimal, and it can't be, can't be a zero. Okay. And then we have an exponent of 10 by which the number is multiplied, right? So thus, the temperature of the sun, 15 million kelvins, is written as 1.5 times 10 to the power of 7. Now, what about this one here? In order to move the decimal place, we have to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 21, 22, 23, 24, 25, 26. And then we finally get there. So it would be 1.673 times 10 to the negative 26, I think, is the number we got to, or whatever number we got to there, right? I lost count. But anyway, there we go. That's how we would have to approach that. Good. Okay. So let's talk about for positive exponents. Here they're asking us to express 1234.56 in scientific notation. Well, first we have to decide what is our n value, and how do we find that out? Well, we know that we have to move this decimal to the left until there's only one number to the left of the decimal. So we know we have to move it all the way to this position here, right, where we have 1.23456, because now there's only one number to the left of the decimal, which is one digit, I should say, not one number, but only one digit should be left to the left of the decimal, and then all the other digits are to the right of the decimal. But the thing is, as we move the digits over to the left, we have to multiply by 10, right? Because as we know, if we go to the left with our decimal, then we're dividing by 10 essentially. And so we have to, in order to keep the same number, we must multiply by 10 so that we're keeping the same number to counteract what we're doing, right? So we're multiplying by 10 and dividing by 10 all in the same step. And so that's just doing nothing essentially, right? Well, other than changing the form, right? Scientific notation isn't about solving anything. It's basically about taking really large numbers or really small numbers and making them into a more digestible form. Which, maybe at some point, you might argue that scientific notation just makes things more complicated. But I think once you get the hang of it, you'll kind of at least start to see what the purpose of scientific notation is and why it's a good thing to be able to recognize in your science textbook, and just to be able to express, large numbers with it in general. But yeah, so let's watch they do it as they do it. They say each time the decimal place is moved one place to the left, we have to multiply by 10 again, right? So they moved it from here to here, and they said, well, we have to multiply by 10 to the power of 1, right? Because we moved the decimal place over 1 to the left, so we've divided this number by 10. To counteract that, we need to multiply by 10. Then they do it again. They go over here again, they multiply by 10 again and get 10 squared this time. And then they do it again. and then now they multiply by 10 a third time. And so the exponent is increased by 1 because we're essentially what we're doing is we're multiplying by 10 again. Every single time we move it to the left, we need to multiply it by 10 to counteract that last moving to the left. The opposite is true if we have to move to the right. For negative numbers, for negative exponents, like when we're expressing 0.00657 in scientific notation, every time we move it to the right and multiply by 10, now we've got to divide by 10 to counteract that. And how do we divide by 10? By multiplying by 10 to the power of negative 1, right? Because 10 to the power of negative 1 is the same thing as 1 over 10, right? And so here they moved it over once and they said, okay, we're going to multiply by 10 to the power of 1 now. Then they move it over again and they do 10 to the negative 2. Then they move it over again and get 10 to the negative 3. And then there's their final answer. And they know they've moved it far enough because now there's only one non-zero digit that's to the left of this number. Very good. So basically, every time we move to the right, the exponent is decreased by 1, and every time we move to the left, the exponent increases by 1. And that's to keep the balance, because at the end of the day, this number and this number, although they look different, they're in different formats, they express the same value. They are the same thing. And same with this one here and this value here at the end. They look different, yes, but they are the same thing. They have the same meaning to them, right? And that's something I want to make extra clear is that finding scientific notation, it's not about solving anything. It's just about going from one format into the other format, right? Much like when we convert, 60 minutes into 1 hour. It's like, well, 60 minutes and 1 hour, they're the same thing, right? They look different on paper. If I wrote down 60 minutes and I wrote down 1 hour, they look different. That's, different format slightly, right? But they're the same, they have the same meaning, right? If I tell you the class lasts 60 minutes or the class lasts 1 hour, well, the class is going to last the same amount of time. Good. All right. So let's go ahead and express each of the following numbers in scientific notation. Okay. So let's start with A. So keep in mind, I don't see any decimal for A at all. So I'm going to assume there's an invisible decimal right here. Now I need to get this number to the point where we only have one number to the left of the decimal. And I have a problem because I have three numbers to the left of my decimal. So that means I need to move the decimal 2 points over to get 2.3. Now, because I moved the decimal 2 points to the left, I need to multiply by 10 to the power of 2, right? Because every time we move our decimal to the left, we need to multiply by 10, right? So we moved it twice to the left, so we multiply by 10 twice, or get 10 squared. And so there's the answer. Now, I will say for numbers like 230, I wouldn't generally, other than in an example like this, I wouldn't expect you to use scientific notation because 230, even though it's kind of a big number, it's a small enough number that it's not really that hard to write 230. Probably writing 2.3 times 10 to the power of 2 causes more confusion, causes an extra step to people that isn't necessary, right? And same with 5,601 and a lot of these numbers actually, but things like 56 million and 14.1 million and, this number here for I and that sort of thing. A lot of these numbers like that, the really big numbers and the really small numbers, it is useful to do that in general terms. However, with some of these smaller numbers, we're just finding the scientific notation because that's what the question's asking, and it helps us practice to do this to understand it. It's not that I would want 230 from now on must be expressed in scientific notation. No, not at all. Okay, so let's try 5,601. Here we have an invisible decimal point here, and we need to move the decimal point over 1, 2, 3 times, right? So we're going to get 5.6. And since we moved it over 3 times, we're going to do multiplied by 10 to the power of 3. Good. All right, now how about this one? We need to move it over 1, 2, 3, 4, 5, 6, 7 times. So we're going to get 1.41 times 10 to the power of 7. Awesome. Now we have 56 million. So if we write that out like this, we would have to move it over 1, 2, 3, 4, 5, 6, 7 times, right? So we get 5.6 times 10 to the power of 7. Good. Okay. Now, what about 2 over 10? Well, 2 over 10 is the same thing as 0.2. So this is another one where certainly in any other context, you wouldn't really have to express this in scientific notation, but we are going to anyway. So to do that, we're going to move it 1 to the right so that way there's only one number or one digit that isn't 0 to the left of our decimal point. And every time we do that, we must multiply by 10 to the negative 1. We must subtract 1 from the exponent of 10. So therefore, it would be 10 to the power of negative 1. Same thing with this example here. We only need to move the decimal point over one place to get 4.5013 times 10 to the negative 1. So we just moved it over once, so just 10 to the negative 1. Okay, what about this one? Well, here we have to move the decimal over twice to get 8.9. And so it would be times 10 to the negative 2 since we moved it over twice there. All right, and what about h? Let's see, 1, 2, 3, 4 times. So that's 2.6 times 10 to the negative 4 since we moved it over 4 times to the right. What about this one here? 1, 2, 3, 4, 5, 6, 7. Well, we're moving it over 7 times. So it's 6.98 times 10 to the negative 7. And then we have 12 thousandth. So 12 thousandths is what? Well, that's going to be 0.012, right? Because this is the tenths place, this place. This is the hundredths place, and this is the thousandths place. So if there are 12 thousandths, right, that's the same as there being one whole, hundredth, because there are 12 thousandths, right? That's the same as there being one full 100 and then two extra 1000ths, right? So that would be 0.012. And so here we would have to move the decimal point over 2 spaces to get 1.2 times 10 to the negative 2. Good. All right, so number 2 says, express each of the following measurements in scientific notation. Speed of light in a vacuum. Oh, that's pretty cool. That's really fast. That's a lot faster than a bullet. Oh, wow. I'm not sure if this is right or not. I'm not a science person, but that's if so, that's kind of crazy. That's kind of nuts. Anyway, let's do what it says though and put it in scientific notation. So we would start here and we'd go 1, 2, 3, 4, 5, 6, 7, 8 over, right? Oh, somehow we got a shape there. Didn't mean to get a shape. But anyway, the point still stands that we'd have to go over, move the decimal point over 7 times to the left, right? So it would be 2.99792,458 times 10 to the negative, times 10 to the power of 7, not negative 7. Or no, I think it's 8 times actually. Is it 8 times? Looks like it. Yeah, 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the power of 8 actually. Good. Meters per second, we'll put in units. In science, they usually like when you put units, so we'll do that. In math, it's good too, but I think especially in science, they really like when you put units. Okay. Number of seconds in a day. 86,400 seconds in a day. Okay. Well, we got to start here and go 1, 2, 3, 4 over. So this would be 8.6 times 10 to the power of 4 seconds in a day. Awesome. All right, the mean radius of the Earth. Oh, that's interesting. I guess the radius of the Earth changes. All right. All right, but regardless, 6,378 kilometers. Well, we'd have to move the decimal over 1, 2, 3 times. We get 6.378 times 10 to the power of 3 kilometers. There we go. All right. And then we have density of oxygen gas at 0 degrees Celsius and pressure of 101 kilopascals, 0.00142 gram g per milliliter. I'm guessing grams per milliliter. Either way, let's assume so. 1, 2, 3 decimal points over, so we'll get 1.42 times 10 to the negative 3, since we had to move the decimal point, over 3 times. Good. And then radius of an argon atom. Oh, very, very small radius. Okay. Which makes sense. An atom is pretty small, so that makes good sense. So we'd have to go over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Ooh, so that's going to be 9.8 times 10 to the negative 11 meters. I assume M is meters. Good. All right, well, there we have it. I hope you learned a lot about scientific notation. And unlike some of the other lessons that really just help you for math, I hope this one helps you in science as well. I think this is a good skill to have, a good thing to know how to do to convert it. But especially because sometimes in a textbook it might use scientific notation. So to be able to understand it properly and having done it, that is going to help you. And so that's really the main goal here, because depending on what field you go into, you might never use it. However, it's good to still understand it so that when you do see it in some textbook or you see it in some written work, it'll make sense. It won't be like, oh, what's this? What does this mean? Why is it being written in this fashion, right? It won't be like that, which is good. Okay. All right, so here's a few more questions that they ask you to do to convert things to scientific notation or convert things out of scientific notation. So I will leave that for the homework. The next thing we'll talk about is operations with scientific notation, which is how we may use this in our math class. All right, good work today, everyone, and I will see you later. Bye for now.